Hello, my name is Aniket Singh. My roll number is 21 ME61R06. I am going to show the assignment for FWS problem. First, we open the ANSYS workbench. Then we will go to the fluid flow fluent. Uh, then we get this type of display where at geometry we click the right click and go to the new geometry formation. Then we go to this page where we first change the unit to mm. Then select the XY plane and generate a sketch. In first sketch, first we in first sketch, first we change the setting. We make grid on, major grid spacing is 10, minor grid spacing is 1, and snap per minor is 1. Then we sketch the circle, then we model the circle of 200 mm diameter and two chords of 144 mm diameter at up and down. Then we extrude this part in the reverse direction. For that we select the sketch one, go to extrude, then in this we add material, and in reverse direction we go to 6 mm depth. After that we create another sketch at XY plane. So and make it look at, we create another sketch for pinhole of tool. So we model, we sketch a circle of diameter 6 mm, and after that we extrude it in the reverse direction, but at this time we have to cut the material and of depth 5 mm. After that we make another sketch for the holder, for the tool shoulder, that in this we sketch a circle of diameter 24 mm. We sketch the circle of diameter 24 mm and then extrude this. In this we only imprint the face, and after when we form the sketch we have to generate the sketch, then after that we have to extrude. Our geometry is done. Now we have to name every surface. So for that we have to go to the tool, name selection. We have to select the surface, then apply. We have to give the name to that and click the generate. So by this we generate the velocity inlet, that is this surface, pressure outlet, that is this surface. FWS tool, for FWS tool we select the pinhole and the shoulder circle, and then the top surface and bottom surface. Side surfaces are selected automatically. Now our geometry is created fully. Then we go to the workbench again, go to mesh, click right click and go to edit. Go to edit. Then we have this type of interface. We get this type of interface. Go to mesh, sizing, mesh sizing. We get this type of window where we change this to name selection. Select the Fsw tool, make the element size is 0.3 mm, and in other case we take also 0.5 mm, but in this case we take 0.3 mm. We take the growth rate as 1.1 mm. Growth rate as 1.1. Then we again click to the mesh, go to sizing, and now this time we go to edge selection, and then we get this type of interface where we select the geometry selection and select this edge. Then in this the element size is 1 mm and the growth rate is 1.2. So now our meshing is done. Then we go to again workbench and double click on setup. Then we get this type of interface. So in this our meshing is done. So in this we got 3,46,997 tetrahedral cells. So in this, in general, uh, we take pressure based solver type and absolute and steady state. Then go to model. We make energy equation on. It takes a bit of time. And then go to viscous, select the laminar, and also viscosity is on. Then go to the material. In this we introduce a material, that is aluminum 6066 as given in the problem. So our material name is A6061. For this, in the given problem, the density is given 2700, and specific heat we take it as polynomial, and coefficient in terms of temperature are given in the problem. We filled it that way. And thermal conductivity, similarly, we take it as polynomial and fill it from the question. And viscosity we take a 999 power law. And, in that we take shear rate and temperature dependence and fill all the values. After materials, we go to the boundary conditions. Then boundary condition, inlet boundary condition. In inlet boundary condition, velocity inlet. Then in velocity inlet, we choose the velocity specification method as magnitude and direction. We take a reference name as absolute, and velocity magnitude is 1.33 mm per second. That is 0.00133 meter per second. And in the direction of x, in the direction x, that is 100. And in velocity inlet, there is no thermal changes. Then we go to the outlet one, pressure outlet. In this, we select the backflow reference frame as of absolute, and the backflow direction specification method as a direction vector in the direction of 100. And there is also no thermal change, it is at 300 Kelvin. Then go to wall. Wall, first we see the FS tool, FSW tool. In FSW tool, first we see the momentum. So the tool is moving and the tool is rotating also. So wall is moving wall, and motion is rotational and absolute motion. The rotational motion is along the z direction, z axis, and the origin is 000, and this is a no slip condition. And in this case, the heat flux is taken to be 0 because at some time, after some time, the temperature is likely equal in the tool and the workpiece. Then we go to the bottom face. At the bottom face, the momentum. In momentum, we select the moving wall at the speed of 1.33 mm per second in the direction of 100, and the motion is translation because the workpiece motion is in translation and it's absolute and no slip condition. And in this, we take the convection thermal condition, and we assume heat transfer coefficient as 10,000 watt meter square per Kelvin. Then go to the top face. we'll go for top surface. In the top surface, in momentum, we select the moving wall, absolute and transitional in the direction of 100, and the speed is 1.33 mm per second. And in thermal, the convection heat transfer coefficient is 30 watt meter square Kelvin. And then we go for wall solid, that is the side face. In this, we go to momentum, select the moving wall, transitional, absolute, and speed is 1.33 mm per second in direction of 100. And in thermal, we select the convection heat transfer coefficient as 30 watt meter square Kelvin. Then we go to the solution method. We select the default method which are given in software. After that, we go to the report definition. In report definition, we introduce that variable which we have to found. So in report definition, we introduce lateral force, thrust force, torque, and weld force. The lateral force, thrust, and weld force are created by force, drag force, and torque is created by force moment report. So as we see, lateral force is in the direction of 0, 1, 0 in the Fsw tool. Thrust force is in the direction of 0, 0, 1 in Fsw tool. Weld force in the direction of 1, 0, 0 in Fsw tool, that is the drag force. And torque is about the axis 0, 0, 1 and moment center is origin. After that report definition, we go to initialization. We use hybrid initialization and click on initialization. Then we run the calculation. We take the number of iteration as 2000 and then click calculate. We get these data. The iteration stops at 416 solution. At 416 iteration, the solution is converged. And we have also show the contour plots. For that, we go to graphics, contour. For showing the contour, we have to add a new surface. Go to the new surface, plane. Tool transfers direction. Method is point and normal. The point is 0, 0, 0 and normal is along 1, 0, 0. Click create. Now we see the temperature distribution along the tool transfer plane. Click compute. Save display. Here we see the peak temperature is 5.91 into e to power 2, that is 591. And for viscosity, see here the viscosity distribution, and in this we can also see these report variables individually, like for weld force, double click on it and compute, then okay. We get here the weld force, that is 14.63 Newton. So similarly we can check for lateral force, thrust force and torque force, and we have some results for 0.3 mm mesh size and 0.5 mm mesh size. Here are the results for 0.3 mm and 0.5 mm mesh size, run time, number of iteration, peak temperature, thrust force, torque, weld force, lift force and number of